All right. My name's Peter Bartlett, and I want to tell you about understanding deep learning. So some challenges that deep learning raises for statistical learning theory. Thanks very much for the invitation to present this talk. All right, so we've all heard about deep learning and its huge success at all kinds of problems, from computer vision to natural language processing. What I'm interested in here is the statistical question of how these methods can take a finite training set, like a set of images with captions, how they can use those to choose the parameters of some big model, and then subsequently predict accurately the label associated with a new image, for instance. So some of the behavior of these methods really seems quite anomalous from the perspective of statistical learning theory. So I want to go through some of the nuances of the trade-offs that arise in classical learning theory. So the key issues in any prediction problem are issues of estimation, the statistical one, computation, and approximation. So estimation is how close the performance of the prediction rule we come up with using finite data, or a finite training sample, is to the best we could have hoped for the class of functions that we're using. The computation issue is being able to efficiently go from a training sample to a good set of parameters of the network, for instance, to solve some sort of optimization problem. And the approximation question is all about how well we can approximate the mapping that we'd like between inputs and outputs, X's and Y's. So, do we have a sufficiently rich class? And there are, of course, trade-offs between these. The richer the class, the more of a statistical hurdle we face in trying to extract useful information from a finite sample. The classical tools that we have for attacking these, for estimation, it's uniform convergence, showing that sample averages approach expectations uniformly across a class of functions that we're working with. We typically like to see our optimization problems be convex ones because we know how to solve them efficiently. And we have all the tools of approximation theory to tell us how well we can approximate certain smoothness classes as we move up in whatever complexity hierarchy we're working with. So what are the classes of functions that are of interest for deep learning? Well, they're these deep compositions of parameterized functions. So each of these FIs in this L layer structure is a map from a vector space to another vector space. And these are parameterized maps. So each FI might be represented, for instance, as you take an input vector X, you multiply it by a parameter matrix Wi, and then pass the output vector component-wise through a scalar nonlinearity like this sigmoid, 1/1 plus e to the minus. Or we might use ReLUs, which have a piecewise linear nonlinearity. So same linearly parameterized component followed by a nonlinearity that has this sort of a form. Okay, so the function is determined by the parameters that appear in each layer. All right, well, I want to start, this is the outline for the talk. I want to start by presenting a little bit about how we formalize prediction problems in a probabilistic setting, a little bit about the classical theory for those probabilistic formulations of prediction problems, particularly for classification, also for large margin classification, which is really a conversion of classification into regression. So for classification and regression. And then we'll see how this classical theory clashes with deep learning practice and some of the anomalies that have emerged from empirical experience. So let's start with this formulation of prediction problems. So setting is we have a sequence of n xy pairs, x1, y1 through xn, yn. The x's are observations from a space capital X. The y's are outcomes from a space capital Y. And our aim is to choose a function that maps from x to y so that for a subsequent xy pair, we'll make a good prediction in the sense that the loss incurred when we predict f of x and the true outcome is y is nice and small. Okay, so what are examples of the loss? Well, we might be considering the 0, 1 loss function. in the case of pattern classification. So for instance, if all mistakes are equally bad, we incur a loss of 1 if we get the prediction wrong. Or for a regression problem where y is the real line, we might use the quadratic loss function, the squared difference between our prediction and the actual outcome y. Okay, we're making a probabilistic assumption about the process generating the data. We assume that these XY pairs are generated IID from some fixed probability distribution on the product space, X by Y. So it maps the distribution of X's and the conditional distribution of outcomes given those X's. And we'd like to accurately approximate that conditional distribution in the sense that we want our risk to be small. We want the expected loss incurred when we predict with the F that we choose to be small, ideally close to the optimal F star in our class capital F that we're choosing functions from. So we write this expectation of the loss using this operator notation. P is our distribution, and we use this function L sub F to represent the mapping from XY to the loss incurred by predicting F of X when the outcome is Y. Okay, and our F star, we're wanting our excess risk over F star to get nice and close to 0. So for instance, in the pattern classification example, the risk is just the misclassification probability if our loss is the 0-1 loss. Okay, so we're going to be using this notation throughout, so you should remember that. One approach to choosing a good prediction rule from a class F is empirical risk minimization, where we choose the function that minimizes the empirical risk, that is the average over the sample of the loss incurred on the n xy pairs. And we write that as, again, using this operator notation, now in terms of the empirical distribution P sub n. Right, so P sub n is the distribution that puts mass 1 over n at each of the xy pairs, the n xy pairs in the training sample. For our classification example, this is just the proportion of training examples that are misclassified. Okay, now I mentioned uniform laws of large numbers. Here's how they arise. We're interested in getting the excess risk of our empirical risk minimizer small. So we want its risk close to the risk of the best in the class, F star. And we can write that excess risk in terms of a telescoping sum like this. The last two terms are kind of easy to deal with. So the sum is just the difference between risk and empirical risk for Fn, the empirical risk minimizer, plus empirical risk minus empirical risk for F star, the optimal, plus empirical risk for F star minus true risk for F star. Okay, so that middle term is a difference of two empirical risks. Well, Fn is the empirical risk minimizer. That last term is the difference between a sample average and an expectation for a single function, the loss incurred by F star. Okay, so we know, we can apply some concentration result to say that this thing is going to 0. That's just a classical law of large numbers. First term is more problematic, right? Because we're choosing Fn to minimize the loss under the empirical distribution Pn, and then we're comparing that sample average to the expectation. So we expect that to be biased. How biased depends on the size of the class F that we're choosing Fn from, in some sense. Okay, so one way to bound it is to take a supremum over that class of deviations between expectations and sample averages. And we're going to write that as a maximum over a class of functions of the absolute value of an empirical process, indexed by that class of functions. So an empirical process is something that maps from an index class, in this case, the class of loss functions, L sub F, to random variables, in this case, the difference between expectations and sample averages. And we want and we're interested in the supremum of that empirical process, the absolute value of that empirical process over this loss class. Okay, so again, keep this notation in mind. We're very interested in these differences of P minus Pn. And we say we have a uniform law of large numbers if the supremum over the class of this empirical process converges to 0 as the sample size grows. Okay, so let's go back to these key issues in statistical learning theory and look at a few classical examples. The first one doesn't really involve any trade-off, at least as I've formulated. It's parametric linear prediction. We're thinking of linear functions defined on some fixed dimensional space Rd, finite dimensional space Rd, and maybe our outcomes lie in some bounded range, and our loss is the absolute difference between the predictions and the outcomes. Okay, so empirical risk minimization in this case is a linear program. All right, it's a convex optimization problem. We're minimizing the empirical risk subject to it just being a linear function. And in order to understand the behavior of this sort of a prediction strategy, we can use these uniform convergence arguments, right? We can look at uniform convergence over the class of losses for these linear functions. And it's pretty straightforward to show that this looks like, this goes to 0, goes to 0 like square root d over n. Okay, d is the dimension here. So as long as our sample size is large compared to the dimension, we're in good shape. As I say, there's no complexity hierarchy. There's no trade-off between approximation and estimation. We're using a fixed class of functions and saying for that fixed class of functions, we can get a uniform convergence result. The d in our uniform convergence bound is the dimension of the class. Okay, we do get some trade-offs if we look at richer classes. So non-parametric kinds of methods, like for instance, SVMs. The class of functions here is again linear, but it's a reproducing kernel Hilbert space, possibly an infinite dimensional one. Our loss in the SVM case is this function that takes value that grows if we have a margin that's less than 1. So we want to be on the not just the right side of 0. So we're solving a classification problem here. The outcomes are plus or minus 1. And we're interested in our real valued prediction y hat having the right sign and being far to the correct side of 0. That's the loss that you use. Turns out that when you minimize the empirical risk with that loss plus a regularization term that depends on the norm squared of the function in this RKHS, then you get a quadratic program to solve. Again, a nice convex optimization problem. But here we can think of this as a complexity trade-off because we could think of that optimization problem equivalently as a constrained optimization problem, one that involves a minimization of an empirical risk over a complexity class that's defined as a ball in the reproducing kernel Hilbert space, a ball of a certain radius that depends on that lambda n, depends on the data. Okay, so here, you can think about solving these problems doing an empirical risk minimization over a ball of a certain radius, over a bigger ball of a different radius, and of course, as you consider larger function classes in this hierarchy, you can get better approximation to the relationship between x's and y's that's of interest here. But you pay a statistical penalty. The larger the class, the more the uniform convergence kind of property gets weaker. You need more data to accurately estimate an element of one of these bigger classes. So there's a trade-off there between the statistical and the approximation theoretic properties. Yeah, so we'll see several examples of that form. And another one here is the again linear, but with this time an L1 penalty. Again, you can think of a regularized empirical risk criterion, which again works out to be a quadratic program in this L1 penalized quadratic loss kind of setting. You can think of that as a constrained optimization problem, a constrained empirical risk minimization problem over L1 balls now in our parameter space. Again, there's a trade-off between the complexity in terms of the radius of that ball and the approximation properties that we see as we move up through that hierarchy, and when we do a uniform convergence argument, we pay a price for working with a more complex class. But we expect to see a trade-off there, that we should be able to approximate more and more as we move up through the class, and so we should be seeing the empirical risk on the training sample going down as we get a better and better approximation to the truth, right? So there should be a trade-off between empirical risk and the complexity. Okay, so what happens when we apply that theory to this classical theory to deep networks? Okay, let's look at a little more in a little more detail at the classification kind of setting. And I want to introduce a specific notion of complexity that arises. It's the right thing for uniform convergence kinds of arguments. And this is the Rademacher complexity. So if we have a class of functions, f, we can define the Rademacher complexity as the supremum over the class of functions of the absolute value of another empirical process, and this is the one that's a sample average here of values of our function on the sample, but multiplied by these IID uniform plus minus one random variables. Okay, so we've introduced another empirical process, and the Rademacher complexity of the class is the maximum over functions in the class of the absolute value of this Rn evaluated at f. Okay, so this is quite an intuitive quantity. You can think of it as the Rademacher complexity as the expected supremum of the alignment between a random plus or minus one vector, this epsilon vector, and the vector of functions evaluated on the endpoints in the sample. Okay, so just to remind you of the notation, we're working with f star as the risk minimizer in our class F, Fn as the empirical risk minimizer, and we saw that we could get an upper bound on the excess risk, the risk of Fn versus the risk of F star. In terms of this empirical process P minus Pn, it's the supremum over our loss class of P minus Pn evaluated at F. Okay, so so the crucial quantity here is this empirical process and its maximum over the class of loss functions. So here's the theorem. We can upper bound the expectation of that quantity in terms of the expectation of the supremum of the Rademacher process. That's true quite generally. If we have a bound on the range of our functions, then we have a matching lower bound, within constant factors and peanuts 1 over square root of n kind of quantities. And these are expectations, but everything is concentrated, right? So deviations between expectations and sample averages maximized over our class are close to the corresponding expectations. And so if we have the expectation of the supremum of the Rademacher process going to 0, that's equivalent to these this uniform convergence kind of property, this uniform law of large numbers. So we really have the right quantity when we work with these Rademacher averages. Okay, let's look at right, I said that. So let's look at this upper bound and the idea behind it. This is not really necessary for what follows, but it's so elegant I can't resist. So this is one slide. You're watching it on a video. You can skip past it if you can't, if you're not interested. It's 2 symmetrization steps. It's really very straightforward. So we write the expectation as the expectation of an empirical average for a new sample. I don't know how it works on the video, but that's covered up for me. So we have this x prime, xi prime, x1 prime through xn prime is a fresh sample chosen from the same distribution, and we've got a new empirical distribution here, Pn prime. And we're just noticing that we can write P as the expectation of that empirical distribution. And we're conditioning on Pn. I want to take just the average of these Pn primes. Okay, so we go do that, and then of course we can take the expectation outside. We get an upper bound, that's an expectation of a conditional expectation. That's just an expectation. And now we're symmetrizing also by defining another Rademacher process with these independent xi primes now. And of course, we can just replace Pn prime minus Pn with Rn prime minus Rn, because the epsilon i's play no role here, right? Pn and Pn prime have exactly the same distribution. If we switched them with an epsilon I, if we switched one component with an epsilon I, it's like swapping an xi and an xi prime. These are completely equivalent. Distributions are the same. In particular, the expectation of this quantity is the same. So we have this upper bound. We can bound that using a triangle inequality, which is twice the expectation of the Rademacher averages. Okay, and the rest of the proof is rather straightforward. All right, so what about the classification setting? Well, when we have a plus or minus one valued class of functions, then the losses that we see, the expectation of the supremum over the loss class is just the expectation over the original class. I guess I'm using a plus or minus one valued loss, so maybe scale everything by a factor of 2. That's a trivial observation that epsilon I times yi has the same distribution as epsilon I without the yi. Okay, and then there's this result that says, well, one way to bound the expectation of these, one way to bound these Rademacher complexities is by looking at the cardinality of the class of restrictions of functions to the sample, right? We get a log cardinality popping in there as in this upper bound for functions that are bounded in range, and this is straightforward proof that just applies Hoeffding's bound on the moment generating function, applies it to the sub-Gaussian random variable epsilon I times f of xi. So there's the clue. It's a pretty easy argument. Okay, so we get this upper bound, but we could write that this is a quantity that has the appropriate distribution. We could upper bound it. There's a parenthesis missing there. We could upper bound it in terms of the maximum over any sample of size n, which is something we call the growth function of that cardinality, maximum of that cardinality, and that gives us an upper bound on the Rademacher averages. And then there's a classical result from the 1960s that we can bound the growth function in terms of the Vapnik-Chervonenkis dimension, which is the largest integer for which the growth function for samples of that size is as large as it can be, 2 to the d. And this is for a class of binary valued functions. And it tells us the growth function grows polynomially with exponent d. So in that case, we get that the Rademacher complexity is bounded by something like square root d over n. All right, plug that in and you get that the risk is no more than the empirical risk plus something that looks like square root VC dimension over n for a binary valued class, plus something small. Okay, so without the Rademacher complexity part, this is a theorem due to Vapnik and Chervonenkis. And it turns out that for uniform bounds, you can't do any better than this. So if you want a result that applies for any probability distribution P, and for all functions in the class, uniform as this is, then this inequality is tight within a constant factor, so it can't be improved. Okay, so what does that mean for neural networks? Well, the VC dimension of neural networks, we'll see some details in a moment, but it increases with the number of parameters. All right, so that's something that's sort of unavoidable. Okay, it depends on peculiarities of the class of functions that's computed by the network, but let's look at some examples. So if we have a class of plus or minus one values computed by a network that has L layers and P parameters, when we work with piecewise constant nonlinearities only, so these are linear threshold units, they output only two values. The VC dimension is within log factors of just the number of parameters P. Okay, that's a result due to Baumanhauser from the 80s. If the nonlinearities are piecewise linear, like these ReLUs, then the VC dimension grows within log factors like p times the depth L, the number of layers in the network. So that's an upper bound, and you can come up with examples to show that you can't do it, that it really is as big as p times the depth. Those lower bounds are actually the best known for richer polynomials, so piecewise polynomial of degree greater than 1, although the best upper bound we know is p times depth squared in that case, within log factors. And when we go to richer functions, these are all based on ideas originally due to Goldberg and Jerram, these piecewise polynomial and piecewise linear ones. When we go to richer functions like sigmoids, we need to use some heavier technology, and we get bounds that grow like the number of parameters squared times the number of computation units squared. And this is a result from the 1990s, and we haven't seen it improve. We haven't seen better lower bounds than something like the p times L for those in that 25 years since. Okay, so I guess just to summarize that slide, the real message here is that everything grows at least linearly with p, and seems to get worse with depth depending on the nonlinearity. Okay, but the growing linearly with p is really as we see something as we'll see something rather fatal. We shouldn't be thinking about these as a fixed complexity class, like the linear functions in a fixed dimension that we looked at. We should be thinking about them instead as a part of a complexity hierarchy. So this was a big motivation behind large margin classification, which is really a conversion from a classification problem to a regression problem. So let me say a little bit about that. So the intuition here is that typically for things like neural networks, we're actually using a real valued function for classification. We're not taking just the plus or minus 1. We're really solving some optimization problem over this class of real valued functions. And that seems to be an important property of the methods that are used with this family of real valued functions. So the prediction is the thresholded value in a binary classification problem at any rate. So when we have an XY pair, we look at y times f of x. If that's greater than 0, then we're getting a correct classification. So this y times f of x is the margin of f on the xy pair. And you can think about a larger margin as somehow a more confident, correct classification. When we minimize some sort of a convex loss like the quadratic loss, that's something that doesn't just get us to the right side of 0, it encourages large margins. So, for classifiers that have large margins, we might expect the fine-grained details of functions to be less important, because they're only important when we're really close to the threshold. So this is very vague and hand-wavy, but you can actually make these sort of ideas rigorous and see that indeed, when you're in a setting with large margins, the fine-grained details are not so important. Here's a very, very elegant argument to show that. So we're going to look at Rademacher complexity for a surrogate loss, a loss that we just make up and put in place of the losses we care about. So this phi sub gamma, we'll fix a constant gamma, which is kind of a margin parameter. It's the loss incurred by predicting y hat when the outcome is y. These are both, y hat is a real value and y is plus or minus 1 valued. So if the sign of y hat is wrong, we pay a cost of 1. And when we have a positive sign, the cost decreases linearly to 0. And when y hat times y, when this margin is gamma, and from then onwards, the loss is 0. All right, so it decreases as the margin increases, goes to 0 at the value gamma. What's easy to see that this margin loss lies between the 0, 1 loss, which is 1 to the left of 0, and L gamma, which is the loss that penalizes any margin that's less than gamma. All right, so it's sandwiched between these two losses. So if we can relate the risk with this Lipschitz loss, phi y, to the empirical risk under the same loss, then we get a large margin bound, right? Because we can upper bound the risk that we care about, the misclassification probability, in terms of a large margin risk, phi gamma risk, I'm sorry. And if that's, nice and close to the sample average, then we can upper bound that in terms of the sample average of the gamma margin loss. Okay, so going through those details, the risk under the 0,1 loss is upper bounded by this this Lipschitz loss, which is close to its sample average. If we have a nice small Rademacher complexity for that class of losses, which is okay. So here we're using a contraction inequality. I'm not going to go into any of the details, but it turns out because this loss is Lipschitz, we can pull the Lipschitz constant out in front of it and compute the Rademacher complexity of the class of functions. So we can pass through a Lipschitz function and increase this Rademacher complexity just by a factor of the Lipschitz constant, twice the Lipschitz constant. Okay, and then we use the fact that this phi gamma is dominated by the margin loss, the gamma margin loss. Okay, so we have an upper bound on misclassification probability in terms of the empirical, the sample average of the margin loss, plus the complexity of this class, scaled by 1 over gamma, scaled by the margin that we're interested in here. So you can think of it as turning a classification problem into a regression problem, because it's the Rademacher averages of this real valued class that become important, right? We've thrown out the fact that we were thresholding functions. We don't have to compute the Rademacher averages of thresholded functions, which turns out something like the VC dimension, square root of VC dimension over n. We can work with the Rademacher average of a real valued function. So we've gone into a regression setting now, and that VC dimension, which captures these fine-grained properties around the threshold, it's no longer important in this setting. Okay, so it's the Rademacher complexity of the real valued class that arises. Okay, so what do these Rademacher complexities look like for two-layer networks? Here's a nice easy example. This is a class of two-layer networks defined on a bounded domain of dimension D. So these are functions where we take a linear function and pass it through a Lipschitz nonlinearity, right? And we have constraints, this vector VI for each of the k units. So the VI has a one norm that's bounded by a constant. The vector of all of these WIs has a one norm that's bounded by the same constant. And we're assuming that this is a one Lipschitz nonlinearity that passes through 0 at 0. Okay, so in that case, the Rademacher averages for this class are bounded by b squared times square root log d over n, something of that order. Okay, and so, plug that in, you can get a bound on the misclassification probability for functions in this class. So uniformly across the class, these things are bounded by sample averages of this gamma margin loss plus this sort of complexity term that looks like 1 over, that should be a gamma squared. There's a typo here. So it's b squared log d over gamma, square root log d over gamma squared n. There's a 1 over gamma outside. Okay. All right, and the proof of this is really elementary. It's just using properties that we can pass constants through the Rademacher averages, right? When we take a convex hull, it doesn't affect the Rademacher average. We've seen you can pass a Lipschitz nonlinearity through the Rademacher average, and so on. So you just keep on doing this, and you get the inequality. Okay, what about deep networks? That in that case, we were relying on the inputs to that layer being uniformly bounded. If we go to deeper layers, we're either relying on the nonlinearity to do that for us. So the same argument works that I just presented there works in a deeper network if we have sigmoid nonlinearities that squash the inputs to each layer. in some bounded range. But when you have things like ReLUs, then you need to work a little harder. You need to keep track of the scale through the network as you go. So this is work that Dylan Foster and Matus Telgarski and I did a few years ago, looking at this is a result that's applicable to ReLU networks. Again, we can get a bound on misclassification probability in terms of this margin loss plus something that looks like L is the number of layers. There's our old friend gamma. There's a square root of n down there, and R here is the complexity term. It's the scale of functions in our network. And what is that particular scale? Well, it's for functions that have, you know, these one Lipschitz nonlinearities in each of our L layers. We have our matrices now of parameters, and we measure the scale of the function by getting an upper bound on the kind of operator norm from input to output, right? We get the spectral norm of these WIs, we multiply them all up, multiply them by all the Lipschitz constants of the sigma i's, which are just one, and then there's a fudge factor, right, that we have to keep track of as we move up through the layers. Okay, and I've you know, the thing to keep your eye on here is this product of the spectral norms, sort of a measure of scale of functions, and you can see that as you have more complex functions, then you're going to get a bigger value up here, but you would expect to be able to do better with the term that measures how well you're fitting to the data. So this proof doesn't use a Rademacher averages argument. I don't know how to do it with Rademacher averages. I can do something that's a little different when we use additional information. There's a result due to Golowicz, Rachlin, and Shamir that uses properties of the ReLU nonlinearity, and they're, you know, very simple, elegant argument for that shows that the Rademacher averages for class of functions that has the Frobenius norm of each of these, right? So it's a sort of tighter constraint now. The Frobenius norm of each of the matrices bounded by B, then you get something that looks like B, the product of all those Frobenius norms multiplied together with a factor of 2, divided by the square root of the sample size. Okay, so just to summarize this large margin classification part of the talk. So we've converted a classification problem to a regression problem by using this Lipschitz sort of loss function that lies in between the 0-1 loss and the large margin loss. For a regression problem, we can think about the complexity of our network as being controlled by the size of the parameters. You know, these various results that I've been presenting for different flavors of neural network are all in terms of the kind of scale of functions we can compute. They don't have to depend on the number of parameters. So if we go back to, you know, a few of these, this one here, for instance, right, there's no k appearing anywhere. This is just b squared, right? We can have these one norms. You know, the dimension on the input here only appears logarithmically. The k there doesn't appear at all, right? Similarly for this one, there's nothing about the width of the network. It's just the spectral norm of the matrices in the network. Same for this one, nothing about the number of entries in these matrices. It's the Frobenius norm. It's just a measure of scale here. It can be independent of the number of parameters. But we see this kind of ubiquitous trade-off between the fit to the training data, in this case in terms of a margin loss, and the complexity. You know, I've written here a complexity penalty sort of as a generic P sub n, right? The complexity of the functions that we're working with. So, you know, we're always seeing this trade-off between performance on a sample and complexity of the functions that achieve that performance. You know, and I guess in the large margin classification setting, you might get a benefit from, even if you have correctly classified all of the samples. So even if the sample average of the 0-1 losses is already 0, you might get a benefit from increasing the complexity by improving this margin, right? Improving the distribution of margins on the sample. So, you know, this is certainly a possibility in this sort of setting, but it's always got this flavor of you know, complexity versus fit to the data in some appropriate sense. Okay, so this is, of course, is just an upper bound. I'm not saying anything about how this approaches the best you could hope for. We're just getting an upper bound, and, you know, what guarantees do you have that that'd be any good? So there are comparison theorems that, at least in a non-parametric setting, talk about you know, how well you can do compared to the best. They relate the excess 0-1 risk to the excess L risk for a big variety of different loss functions. So, you know, there's more you can say in that direction. Okay. So just to summarize the sort of application of this classical theory to deep networks, it's really a story of trading off fit to the training data with complexity. You know, at least once we move beyond these combinatorial dimension sort of results, right? And there are various complexity measures that are suggested by tools from empirical process theory. Okay, in the classification setting, we typically have this kind of, you know, number of parameters constraint. We're thinking of that as a monolithic function class, and we want a uniform convergence result across everything we can compute with networks of a certain size. But when we move to large margin classification and regression problems, we do get this sort of complexity hierarchy that's defined in terms of the scale of the parameters that we see. You know, it might be things like products of operating norms in those two cases. Okay, so that's a thread, you know, that arises in the classical theory that we see in this application of it to deep networks. But it's not so consistent with what we see in practice, right? So in practice, there are some anomalies, some strange things that people have observed that really are rather surprising from the perspective of statistical learning theory. So let's go through a few of those. First of all, you know, so people say, oh, deep learning methods are amazing. They work with a number of parameters that's bigger than the sample size. Okay, you know, that just means it's a non-parametric method. This is you know, also true of SVMs, also true of high-dimensional linear regression when you impose L1 penalties. So it's just essentially any non-parametric method you have this this kind of property. You know, you can control complexity in some other way besides just keeping control of the number of parameters. So, for instance, the scale of the parameters. So there's nothing striking about that observation. Deep learning methods minimize empirical risk with little or no explicit regularization. Okay, but, you know, we've known for decades about implicit regularization. Early stopping in gradient methods, for instance, has been studied forever. You know, all sorts of work of that kind in looking at the behavior of things like gradient methods for RKHSs. Deep learning methods find a perfect fit to the data. So, you know, and no matter what the data is. So, okay, you know, if you find a function that's not too far out in the complexity hierarchy and it fits the data, so it has an empirical risk that's 0, then, you know, maybe that's not too surprising, right? You've got good prospects then. If you're not going too far out in the complexity hierarchy, you should be able to prove a uniform convergence result that says, okay, the expectations of sample and sample averages are close across this member of the complexity hierarchy. So the expectation of the loss should be near 0 too. So the really surprising thing is when you can find a perfect fit to noisy data. You know, we shouldn't expect a low complexity solution in that case. This really goes against the statistical wisdom that we're all familiar with, right? So finding a perfect fit to noisy data is something that's really striking, right? And being able to predict, I should say, and being able to predict accurately despite that. Okay, so this is the empirical observation. Deep networks have been trained to 0 training error for a regression loss, right? So no room for this large margin sort of argument with near state-of-the-art performance, even on noisy problems. So here's a particular example that this group at Google looked at a few years ago. So on the x-axis here is the proportion of labels that are corrupted, right, from 0 to 100%. The top graph shows how long it takes to, they say, overfit, get a perfect fit on that corrupted sample. All right, takes a little longer for, and this is the different colors are for different kinds of networks. Takes a little longer for noisier data, but you still get to this perfect fit, and then the test error rather strikingly degrades, but not horribly, right? We know that we've got significant noise here. We're getting a perfect fit to that noise, but we're only getting, you know, a slight degradation of the test error. That's really striking, right? We're fitting noisy training data that should require a very high complexity, and we don't seem to be paying a price for that complexity. So we're certainly overfitting, fitting better than we should expect, getting zero empirical loss when the best possible empirical risk, when the best possible true risk is, you know, 10%, whatever, some significant, at some significant level. But that overfitting seems to be benign. It doesn't seem to be hurting prediction. And there have been a bunch of other observations of this kind, you know, over the time since then. So, you know, this is a really striking phenomenon. So as we've seen, we're always aiming for a trade-off between fit to the training data and the complexity of the prediction rule. But here we don't seem to have that trade-off, right? And whether that trade-off involves the norm of a parameter vector or the product of spectral norms of weight matrices or you know, whatever, we expect to see that trade-off. As we get a better fit, we should be allowing more complex prediction rule. But here we've got, you know, the perfect fit. Okay, and you know, there are a bunch of examples like this. Sasha Rachlin put these together. You know, textbooks that we use for our classes to explain to everyone that, you know, we shouldn't fit too closely, shouldn't fit the training data too closely. We won't generalize well. Interpolating fits are not reasonable ones. They're not, hence is not a reasonable estimate. You know, this is routinely taught in undergraduate classes. So this really does seem to be a new statistical phenomenon. We're getting good prediction with very small training error on a noisy problem. Statistical wisdom says our prediction rule shouldn't fit too well if we want to predict accurately, but deep networks are trained to fit noisy data perfectly, and they do predict well. Okay, so you know, this is quite exciting, and it was the topic of you know, this phenomenon really rose to prominence at a program on foundations of machine learning at the Simons Institute back in spring 2017. So, you know, and since then there's been an enormous amount of work in this direction. Misha Belkin, Sasha Rachlin, a bunch of other people, Andrea Montanari, Daniel Su, a whole lot of people have come up with a whole lot of different perspectives on this phenomenon in different settings. So things like analogs of nearest neighbor methods, kernel smoothing methods, kernel regression, linear regression in various cases that are related to deep learning, and so on. So, you know, lots of different settings where people have studied, often under, you know, specific canonical kinds of models. You know, the data is generated in such and such a way, with X's and Y's related in such and such a way, and here's what we can say about performance in that setting. I mean, in some cases, much more general results, but many of them have this flavor of, you know, work with a very specific model. So what I want to talk about here is the case of linear regression, where we have a rather complete understanding of the statistical question, rather complete understanding of this benign overfitting phenomenon in a linear regression setting. You know, it's not deep networks, but it's a step along the way in understanding a phenomenon that has emerged out of deep learning. Okay, so let me tell you about the setting and in particular the notation that I'll be using here for these linear regression problems. All right. So our space X, we can think of as a Hilbert space. If you want to think of it as a finite dimensional vector space, that's great. I'll actually be using matrix notation as if the elements of X are, finite length vectors. Our space Y is the real, so the outcomes are real numbers. We're trying to predict real numbers using linear functions. Our XY pairs have a linear relationship between them. The conditional expectation of Y given X is X transpose theta star for some fixed vector theta star in our Hilbert space, finite norm vector. Our XY pair is mean zero and sub-Gaussian, and it needs to satisfy a small ball condition. Okay. We'll introduce some terminology, some notation here. Sigma here is the since X is mean zero, sigma here is the covariance matrix, and the lambda i's are the eigenvalues of that covariance matrix, written in decreasing order, right? So lambda 1 is the biggest one, then lambda 2, and so on. So, these are in red. These are crucial for everything that follows. Lambda i's play a big role in what's going on in benign overfitting and linear regression. That theta star we've met already. It's the minimizer of the risk over this class of functions, the linear functions. So it achieves the minimum of this expected squared error of our predictions. And we write that minimal expected squared error as sigma squared. All right, so sigma squared, this notation is all going to come up, right? The lambda I is the sigma, the theta star, and the sigma squared. So remember those. We have our estimator here is a very specific minimum norm estimator. Why are we using a minimum norm estimator? This seems to be a very reasonable thing to do. You can think of it as starting off at theta equals 0 and doing a gradient flow using the squared error on the training sample. Perform a gradient flow in that objective. You'll arrive at the minimum norm parameter estimate that fits the data perfectly. All right, so think about the data as a matrix of n rows. We'll write it using this matrix notation. So n elements of our Hilbert space. The outcomes y, we'll put in an n vector. And our estimator is the one, I've written it here explicitly in the usual least squares sort of X transpose X inverse X transpose Y. Of course, this is just an X pseudo inverse Y, but I've replaced the usual inverse with a pseudo inverse. And of course, this thing finds the minimum norm parameter vector that minimizes the error on the training sample. Okay, now if the minimum norm estimate is non-zero on the training sample, this might be a singleton set, but we're interested in cases where it's typically a whole subspace of values, these thetas. Okay, so let's think about this minimization problem, minimizing the norm subject to this minimization of the empirical risk. We can think about that, in these different ways. It's just like those optimization problems we saw as classical examples of the theory earlier. So there's the regularized case where we minimize empirical risk plus a regularization penalty. We're penalizing the norm squared of our parameters. We could equivalently think of that as minimizing the empirical risk subject to a certain constraint. And of course, there's got to be a relationship between the radius of the ball that the thetas come from versus the regularization parameter. Or we could think of it as minimizing the norm subject to a constraint on the data fitting term, the sample average of the losses. The striking thing about the situation we're talking about is that we're considering the case where this constraint on the fit to the data term is too small, right? We're thinking about the overfitting regime where that quantity C is much smaller than, the best we could hope for. Best we could hope for should be something like the noise level, right? The minimum of the expectation, which is this sigma squared. But we're thinking about cases where the average on the training data is well below that. Think of C equals 0. So that's the overfitting regime, and we're asking the question, when do we predict well in that overfitting regime? Okay, so the criterion of interest here is the excess prediction error. We'll write it as R of theta hat. It's the expected squared error versus the best possible sigma squared, this minimum over all theta. We can write that in terms of theta star. And when we do, it's an easy calculation to see this is just a certain notion of the error of our estimate theta hat compared to the truth, the theta star. And you'll see, this is the importance of those lambda i's, right? The lambda i's tell us what directions in parameter space are important for estimation. Large values of lambda mean we better get theta hat to be an accurate estimate of theta star in that direction. Small values, it's not so important, we can get things wrong. Okay, so this is one role that the lambda i's play. All right, so here's the characterization of benign overfitting in the case of these linear regression problems. Okay, so we've got a theta star, a sigma squared, and a sigma, the optimal parameter, the noise level, and the covariance matrix. We want the covariance matrix to have n directions so that we can find a parameter value that has 0 empirical risk. Now I'm going to introduce a couple of notions of effective rank, and I'll define them on the next slide, but for now, let me just wave my hands. So K star is the smallest value of K where the effective rank of the covariance matrix when we eliminate the K heaviest directions. So throw away the directions corresponding to the K biggest eigenvalues, look in the orthogonal subspace, and in the covariance in that orthogonal subspace. We're interested in the effective rank of that covariance matrix, right? So what does the effective rank of the remaining eigenvalues look like? K star is the smallest K for which that effective rank is big compared to the sample size. Okay, so that's K star. It depends on a certain notion of effective rank. Then you could say with high probability, the excess risk is bounded by, I'll say what the bias is in a moment. There's a bias term and there's a variance term that depends on the noise. The variance term has this K star over n. So we better get to a nice big rank early on, right? With K star small compared to n. And then the variance term has n over capital R K star sigma. So this is another notion of effective rank. Again, we're eliminating those first K star directions, looking in the orthogonal subspace and looking at a certain notion of effective rank there. So we want that to be big compared to n. Okay, that's our upper bound. And okay, so there's the bias. It depends on theta star, depends on these eigenvalues beyond. That should be a K star here everywhere. Okay, I'll say a little bit about that later on. For the lower bound, we need some additional conditions. If you have your x's, so this is think of it as an example that shows that you cannot improve on this upper bound. This upper bound is really quite general. The lower bound is under the additional condition that you have a lot of independence. So the x's are a linearly transformed version of a vector that has independent components. To get the bias term in the lower bound, we need to look at a sort of average of optimal parameter vectors where we have equally likely directions, equally likely sign flips in each component. And then in that case, this expectation is taking these random sign flips into account, blah, blah, blah. We get a family of examples where you cannot improve on these terms by more than constant factors, right? That's the kind of bottom line, that this bound is tight. Okay, so what do these little rk and capital RK star effective rank quantities look like? So the lambdas are the eigenvalues. Little rk is the sum when you eliminate the biggest k eigenvalues, look at the sum of the rest versus the largest of the rest. So this is an L1 norm over an L infinity norm, right? It's looking at how many of these can we fit in the tail, right? And remember, we want, when this thing is big compared to n, that defines k star, right? When the biggest one in the tail fits, more than n times into the rest of the sum of the rest of them. Capital RK is another notion of effective rank, but it has the one norm squared on the top and the two norms squared on the bottom rather than the infinity norm. Okay, so they're just two different notions of effective rank. They're related to each other. Always bigger than one. Capital R is bigger than little r. Not too much bigger, smaller than little rk squared. These are sort of elementary inequalities to prove. That's a bit of an exercise. Okay, so with those notions of rank, you can see the rank here is never bigger than the actual number of parameter directions that you have left after k, right? So certainly if you want to have RK star big, you better be in a dimension that's big compared to the sample size, right? You have to be in a high dimensional space compared to the sample size for this term to ever be small. Okay, so that's the first thing to notice, but actually RK, for it to be big, you want a lot of these directions, and you want them all to be sort of roughly the same level. You want some symmetry there to have a big value here. If these drop off quickly, then you're in trouble trying to have this as a big value. Okay, so the mix of eigenvalues there is determining how it plays two roles in this problem. It comes in, we saw already that it comes into, how the errors in our estimates affect the prediction accuracy, but it also determines how the label noise gets spread out through the parameter space. And it's the interplay between these two that we're seeing in this sort of, in this theorem. The message there is that we have to distribute the noise energy across lots of unimportant directions. Okay, so you have to be in a very high dimension parameter space to have benign overfitting. Okay, lots of non-zero eigenvalues, a large number compared to n. Their sum should be small compared to n. You want the total scale not too bad. And the number of these small eigenvalues should be large compared to n. And more asymmetric is worse. So symmetry is good out there in the tail. Okay, let me say a little bit about the proof ideas. There are kind of two pieces I already mentioned. There's a bias piece and a variance piece. The bias piece arises from the signal that's there, the x transpose theta star. The variance piece arises from the noise, the difference between y and x transpose theta star, its conditional expectation. The signal piece, we get a distorted view of theta star in our estimate theta hat because the x's that we see in the sample, aren't exactly the covariance of x, but this is pretty innocuous, the nature of the error here, even though we're in a high dimensional space. The variance part is more difficult, right? And that's because we're taking all of the noise and injecting it into our parameter estimate theta hat. Okay, so that's problematic. We're asking when we can hide that label noise in our parameter estimate without hurting predictive accuracy. Okay, so just to take you through the steps quickly, we split the outcomes y into the signal part and the noise part, x theta star and epsilon. We can think of the two parts of y and their impact on theta hat. Okay, split them up and look at the excess risk. We get two pieces. The first piece we're going to deal with as a bias piece, and the second piece is a variance piece. In terms of understanding what goes on with the excess risk, we can split our covariance matrix, do a spectral decomposition of our covariance matrix. We can split these things up into the heavy directions, the big values of lambda I, and the light ones, the smaller values. Turns out that this effective rank condition is what we need to ensure concentration of the smallest eigenvalues of X transpose X, right? So the smallest positive eigenvalues. We have lots and lots of zero eigenvalues because we're in a very high dimensional space and we only see n directions. But the smallest positive eigenvalues are all going to end up being concentrated once we have this condition on the effective rank satisfied. Turns out they're concentrated around this value, the sum of the tail of our eigenvalues. So if we look at the Gram matrix, the matrix of inner products, it's got a lower bound, right, in terms of this row. All of its eigenvalues are at least as big as rho. So you can think of that as, when we take this pseudo inverse, there are some directions that are zero. Fine, we ignore those, they just disappear. But all of the n non-zero directions, it's as if we've got a lower bound in those directions of rho. So when we take the inverse, the pseudo inverse or the inverse in those directions and zero out all the others, we're not blowing things up too much if rho is not too tiny. Okay, this is a lot like a ridge regression setting where we add a regularization penalty. Okay, and our minimum norm estimator, you can track where the energy from the noise goes into the parameters and into the error of the parameters, right? So we get some energy from the noise, it gets multiplied by x, so scale differently in different directions. If we're looking at a eigenvector direction vi, then we get noise energy proportional to n times lambda I. That's scaled by this pseudo inverse by no more than 1 over rho squared because we're talking about energy. The impact on the prediction error is scaled by another lambda I. And so we get a bound on the impact on the prediction error in that direction of n lambda I squared rho to the minus 2 in a very vague sense. Turns out we can do better in those k-star heavy directions. You can always upper bound those by 1 over n, add that all up and you get k over n plus n over this effective rank of sigma, and that's the variance term. Okay, so that's the characterization. One thing to point out, this k star over n term in the variance term, it's really the same as the variance term we see in a parametric linear regression setting when we're working on R k star. We saw something of that flavor. We were working with absolute loss, so we had a square root there. Here, square loss, we lose the square root, but it's still the k star over n. Same thing there. It's as if we're in this finite dimensional setting, and that's all we have to estimate. The bias term is actually suggestive of that, right? It's really an effective dimension. When we look at this component of the bias term, it's exactly the bias that we would see in an estimator that just predicted 0 in the orthogonal subspace from k star plus 1 onwards, right? We're counting the error as if we predicted 0 out in that subspace. So we're really getting nothing from our estimates beyond k star. Okay, and and that's there in these upper and lower bounds. That's real. Okay, well, we can ask for these kinds of, so we have a handle on the risk. We can ask the excess risk. We can ask, well, for what kinds of eigenvalues do we get nice predictive accuracy? Do we get our excess risk going to 0 as a function of n, right? It turns out if you look at the infinite dimensional setting and a certain rate of decay of the eigenvalues, it's a very peculiar case, right? It's only the 1 over I times log to some 1 over log to some power of I that we get this sort of convergence to 0. So it seems like the lambda I should be just at the edge of being summable. So that looks like something really rather unusual. Turns out if we're working in a finite dimensional setting, finite but large, it's a much more generic phenomenon. So if our eigenvalues decrease rapidly, but there's always this sort of minimal level out to some dimension Pn, then we get benign overfitting as long as Pn is big compared to the sample size, and the energy that we've got here that's uniform across all directions is small compared to the sample size, but not too small. Okay, and you can quantify that. Same thing if you talk about, slow eigenvalue decay, but truncated at some Pn, some dimension, finite dimension, and then 0 after that. So in the finite dimensional setting, as long as things decay slowly enough, if we're in a high dimension, we're good. We get benign overfitting. So this seems like, in finite but very large dimensions, seems like quite a universal phenomenon. Okay, so to summarize this part of the talk, benign overfitting, we're in this overfitting regime. Interpolation is the extreme of it, right, where we're fitting the training data exactly. That's far from these kinds of trade-offs between fit to the training data and complexity that we saw in the classical setting. What's necessary and sufficient in linear regression for benign overfitting is a long, flat tail of the covariance eigenvalues, right? The noise is being hidden in lots of unimportant directions. I think that's the intuition. It relies on lots of roughly equally unimportant parameter directions. The finite dimensional aspect seems to be important, right? If we have infinite dimension, it's hard to make our eigenvalues decay in just the right way to get benign overfitting. If we truncate at some finite but very large dimension, it seems like a much more generic phenomenon in this minimum norm linear regression setting. Okay, you can extend this to minimum norm ridge regression, where, we're thinking about the smallest norm that minimizes this setting with a ridge regularization, an L2 regularization. So if lambda equals 0, that's the same problem. If lambda is greater than 0, of course, this argmin is unique, but it covers that range of solutions from a very small value of lambda right up to a appropriately regularized value of lambda. We can get tight bounds on bias and variance for any value of lambda. The effective ranks just get replaced. The L1 part gets a lambda added to it in both cases. Surprising thing is, in some cases, you can have the optimal lambda being negative, right? So you get, a negative lambda actually decreases the bias in some cases without significantly affecting the variance. So this is kind of an interesting, an anomalous sort of situation. It's not what you would expect from classical analyses, for sure. Okay, so here's the result in that setting. We're replacing these effective ranks by the things that depend on lambda. They have this extra lambda blowing things out, making things better conditioned, and you get exactly the same result in that richer setting. Okay, so that's with Alex Sigler, that last result. Okay, so let me look at sort of connections between these two. So the last section here is on barriers to analyzing benign overfitting. So it's looking at why some of these classical tools might not be at least directly applicable. Okay, so the first of these is concerned with uniform convergence and why it might not be directly applicable in a benign overfitting setting. Okay, so so here we have, let me introduce a few definitions to explain this result. So we've got a loss, we've got an algorithm that takes a sample of size n and it returns h sub s. Then we can define the generalization error of that algorithm as the smallest value that we can plug in here, so that the probability over our draw of the sample of size n, that the risk minus the empirical risk is less than this epsilon is at least 1 minus delta. All right, so that's a generalization error, just a bound between sample averages and expectations for the function our algorithm returns. Let's define the uniform convergence bound as the smallest value that we can get as an upper bound on some uniform convergence property. And this is defined as, there exists a set of samples of length n that have probability at least 1 minus delta. And H sub delta is all the functions that our algorithm might return for a sample from this high probability set. So anything we can define that has this that has this high probability property, we want to look at maximal deviations between expectations and sample averages, right? Okay, so so the supremum over these samples and these H's of the deviations between expectations and sample averages. Okay, that's our tightest uniform convergence bound for, you know, the set of functions that we define that our algorithm returns. Okay, so the rather striking result due to Nagarajan and Coulter is that for a loss, for that gamma margin loss L gamma, there's a probability distribution on X, and X is a vector space, and Y is plus or minus ones, and a particular algorithm that returns, you know, one of these HSs, so that this uniform convergence bound is terrible. It's at least as big as 1 minus epsilon, where epsilon can be made nice and small, right? So this is the generalization error. It can be really small, but the best uniform convergence bound that you can come up with, you know, no matter how you choose the events, the high probability events you want, you can't get this thing any smaller than 1 minus epsilon. Okay, so you know, this is a very nice example. It's probability distribution and an algorithm. The probability distribution is on this vector space. Let me say a little bit about that. It's on Rk by R d minus k. So it's a d-dimensional space. The first k variables are signal variables, right? Y is determined as a function of those. And there are lots and lots of, whoops, and there are lots and lots of noise variables here. Okay, so you know, these are irrelevant to the classification. The algorithm is just naive Bayes, and it achieves a small generalization error, right? Sample averages are like very small with this algorithm, and the expected loss is nice and small. Proof idea here is that you know, as I say, you get a nice small margin, risk, but for any sample S, you can come up with a sample S prime by reversing these noise variables, reversing the sign of the noise variables, so that the sample average on the S prime sample is really bad, right? You're looking, it looks terrible on that sample. And the symmetry of the distribution that generated these X's is such that that doctored sample is likely to fall in your high probability set. You know, so it's a rather neat argument to show that any uniform convergence result, if you want to come up with a bound on performance based on uniform convergence over the set of functions that are produced by this particular algorithm, with this distribution, those bounds are necessarily going to be loose, right? Your uniform convergence bound can't be a small thing. Okay, let's move on from uniform convergence bounds to any kind of model dependent bound. We're going to go to the linear regression setting, and this is work with recent work with Phil Long. So here we're thinking again about the least norm interpolant in a linear regression setting. We're going to define a uniform model dependent bound as a function, epsilon, that depends on the theta hat, the particular linear prediction rule we come up with, depends on the sample size, depends on the confidence. And it's a uniform bound in the sense that for all distributions that are nicely behaved, what does that mean? I want mean 0, and I want them to be sub-Gaussian with a fixed constant, let's say 1. Okay, so for all those distributions, I want the probability that the excess risk of theta hat is smaller than my bound is at least 1 minus delta. So it's a good bound in this good bound on the excess risk. Epsilon we'll call bounded anti-monotonic if, when we increase the sample size from n1 up to 2n1, we don't increase our bound by very much. Right? So a bigger sample, you would expect a bigger sample size to help. Here we're saying it can't hurt by too big a constant factor if we're increasing the sample size by no more than a constant factor. Okay, so that's bound, a decreasing function of sample size is certainly bounded anti-monotonic. We just want it not to increase too rapidly. Okay, and the other terminology that we need is this notion of a strongly dense set. Here we've sort of got a notion of the density of a subset of the natural numbers that says, if you're around a point n and you look at a set around that point of scale, something like square root of n, the proportion of those numbers is at least beta. No matter what n is, if the size of the set around it you consider is of order of square root of n, then the proportion of those guys is at least beta. So we have a beta dense set. That's what that means. Okay, so now I can state the theorem. As I say, this is with joint work with Phil Long. So there are probability distributions on RD by R, and these are, really nice distributions. The X is Gaussian, the Y is sub-Gaussian, has continuous distribution. And for these distributions, if you have a bounded anti-monotonic uniform model-dependent bound, then for all delta, your least norm interpolant for large enough n is nice, right? The excess risk of your least norm interpolant with high probability is going to 0 like 1 over square root of n. So, we're in a benign overfitting setting for the least norm interpolant in this linear regression problem. Okay, on the other hand, the set of sample sizes n for which, when you choose your sample from Dn and the sample of size n, the probability that you're bound, this uniform model dependent bound, is bigger than a constant is at least a half. So it's a terrible bound, right? Well, actually, I left out the punchline. The set of n for which this happens is roughly 1 minus delta dense. So if you look at the proportion of values of n in any kind of size square root n region around n, proportion 1 minus delta of them will give you a terrible value of this model dependent bound. Okay, so most values of n in that sense, most values of n have a terrible, a bigger than a constant with significant probability. And yet, if this is supposed to be an upper bound on the excess risk, we're upper bounding something like 1 over square root of n with something like a constant. So any bounded anti-monotonic uniform model dependent bound is bad in this sense. Okay, these are quite natural joint distributions on the training examples, and the only real condition here is bounded anti-monotonic. We're saying that these epsilons can't increase too quickly with n, right? And under that condition, they have to sometimes be very, very loose. Okay, let me say a word about the proof idea. It's based on this intuition that if you're working with an interpolating prediction rule, it interpolates the data, and the data is noisy. So you know that everywhere on the training sample, you have a bad estimate. It's sort of order of sigma away, where sigma is the noise level. It's order of sigma away from the conditional expectation at that point. Okay, so on the training sample, our estimate is a bad one. It's certainly not approaching the optimal prediction. Away from the training sample, we might be doing really well if we're in one of these benign overfitting settings. So that's sort of something to worry about. And the proof of this impossibility of these model-dependent bounds being effective is a kind of Poissonization approach. It shows that you can't really distinguish between two situations. One where the training sample forms a significant fraction of the support of the distribution, and so you know, you're going to do badly because you're fitting to that training sample, and one where you're in a genuine benign overfitting situation, and the training sample's got measure 0, and you know, your true risk is approaching the optimal. Okay, so if you've got a bound that's valid in both cases, you know, it has to be nice and big here to account for the bad performance on those training points. So it's got to be loose in the second case. Okay, so let me summarize. The first part of the talk was about applying the classical statistical learning theory to deep networks. And there the story is about trading off fit to the training data and complexity. And the notions of complexity, you know, are suggested by all these tools from empirical process theory. But I think you know, working with complexity hierarchies, they're typically of the form of, you know, the scale of the parameters affect the complexity of the class. And that's something to trade off for the fit to the training data. You know, that classical story really doesn't fit with what with some of these empirical observations, in particular this phenomenon of benign overfitting. So I told you about an investigation of benign overfitting in a specific setting. It's not deep networks, it's linear regression. And there, you know, we really are seeing a case where you're fitting perfectly to the data but predicting accurately. In the linear regression setting, we could characterize when that would work. It needs this long flat tail of the covariance eigenvalues. So lots of equally unimportant parameter directions, and that's a place for you to bury the noise, a big subspace for the noise to go. And having a finite dimension seemed to be important in that setting. So, you know, you want to have a very large but finite dimension. Okay, and the last part of the talk was about analyzing benign overfitting and you know, barriers to these sort of classical tools being directly applicable to the analysis of this phenomenon. So we saw that a direct application of uniform convergence bounds, you know, this result of Nagarajan and Coulter showed that could not work for, you know, a specific rather nice simple example. And we saw that if we wanted a model dependent bound for the linear regression setting, least non-linear regression, then, you know, under some rather mild condition on that bound, it's also got to be something that can't be very effective for analyzing benign overfitting. All right, and of course the big challenge here is moving from these nice analytically tractable settings like linear regression to understanding what goes on in deep networks. Okay, thank you.